Okay. So what happens here is that you have V and B is in perpendicular to each other. And like I said, a cross product is a mathematical interpretation of we trying to find the result of a vector that are perpendicular to each other. That's why we have VB sine theta. So the angle between two vectors that are perpendicular to each other is 90 degrees. Okay, so sine 90 is actually 1. So basically at this point, or in fact any point under the surface, you will always have V cross B equals to VB sine 90, which is equals to VB. Okay, so whether the coil is here, okay, so whether the coil is here, here, or here, or here, or here, V is always this direction, right? And B is always perpendicular to the surface, okay? So you will always have VB perpendicular to each other, alright? So any point under the surface of the pole, okay, because north is north pole and south is south pole, so we call this machine a two-pole machine, okay, because you have two poles, north and south. So if the coil lives or located under the pole, you will always have V cross B equals to VB sine 90 degrees, because V and B are perpendicular to each other, which is equals to VB. And that is simply dot with L lah. So multiply with length. Alright. Okay. So that's how we come up with these voltages. Okay, the induced voltages. So BA and CD are the sides that are perpendicular to that are always perpendicular to the magnetic field lines. Okay, so because of that, you will have VB times L. Okay, so BA and DC has VBL. Alright, but this side and this side is always parallel with the magnetic field, right? So if we go back, we know that this is AD, right? This is AD if we're looking from the front view, and B is this way, right? So obviously the movement is obviously the line is parallel with B. Alright, so if it is the movement is parallel with B, so basically the cross product will become 0 lah. Alright, so therefore we will have V cross B sine 0, which because parallel is like 0 degrees between each other, so you will have EDA or AD and BC equals to 0. So when we add up all of them, you will get 2VBL. Okay, so V here is basically a linear velocity, right? Linear velocity, which is V. But since in the machines are rotated, right? So the rotor is rotating. So the way we can actually do that, we can actually interpret to much easier interpretation of, for example, RPM, revolution per minute, or radian per second, is to translate the linear velocity into rotational velocity W. Okay. So how to do that? We know that V is actually equals to R omega. Okay. So why? Because if you can still remember in our elementary maths, if we want to find a sector of circle, okay, we know that the sector length here is equals to R theta, right? So S is equals to R theta. So if we differentiate this length over time, we're looking at this length over time, then we know that we can also do the differentiation from the S side and from the R theta side. Since R is a constant, so the ddt is on the theta only. So ds dt is actually a translational velocity, and d omega theta dt is actually omega, or rotational velocity. Okay, so this is how we get the equation. Now if we replace v with r omega, now you will have a new equation. Okay, so we know that under the pole faces, okay, under the pole faces, this is the pole faces, okay, this is the pole faces, this is the pole faces. If the coil are under the pole faces, the induced voltage is 2r omega bl. Alright, so from here we know that we can also represent, okay, the equation, or simplify the equation. Right now we know that the induced voltage is depending on the radius, okay, the radius of the rotor, the speed of the motor, and then the magnetic field density, and the length of the rotor. Okay, we can actually represent that into another variable, which is flux. Okay, so the total flux inside the machine. Okay, so how to arrive to that is that we try to represent the surface area or a pole surface area as pi RL. Okay, so how do we get this? It's basically because we assume that the rotor itself is cylindrical. Okay, so the when the rotor is cylindrical, you know that the rotor surface area, or the cylinder surface area, is 2 pi r L. Okay, so since half of the rotor is actually under one pole face at one time, so the pole surface area is actually pi r L, because you divide the surface area of the rotor, that cylindrical rotor, into 2. Okay, so if you replace if you replace AP, okay, so AP is pi r, oh my god, AP is pi RL. Okay, so then R is actually AP over pi L. Okay, so if we replace this new equation inside here, what we will get is 2 over pi AP. Okay, L you cancel with this L. Alright, so we will left with B omega, and we know that A times B, okay, the area, the surface area, times the magnetic field density is actually a flux. Okay, flux is B times A. That's why we get this equation, right? So eventually what you have is that the induced voltage of the machine will depend on the total flux inside the machine, the speed of the rotation of the rotor, as well as this constant 2 over pi. Okay, so this 2 over pi, because there is one single coil. If you have multiple coil, okay, with multiple arrangement, you will have a different constant there. So we can reduce the dependency of voltages that we can get from a DC machine into a machine constant because of the construction, the total flux inside the machine, as well as the speed. So basically, if you have larger speed, you will get more voltages. Or if you have more flux inside the system with the same speed, you get more voltages. Or if you increase the constant, means you put more coils inside the system, you will get more voltages. Right? So that is the principle of operation of the DC machines to get the induced voltage. Okay, so in the case of generator, when you're trying to get a DC voltage out of the rotating loop, you need a commutator. And we see from the previous video how the commutator works. It maintains the line of current into simply one side. Okay, so without commutator and brushes, what happens is that as it rotates, because it changes like the polarity of the, so the coil, okay, originally it was under the north surface, in which B is this way, right? And then as it rotates, okay, this side CD will become at this side, and it will be under south side, in which B is that way. Okay, not that way lah. B is still that way, but you're facing the other direction. Okay, so what happens is that the current will change direction. So you will have this shape, okay, coming out from the coil at the end here. Okay, so without commutator, we will have an AC voltages. Okay, but if you want a DC, then we need the commutator, right? So that when it brushes over, when the commutator brushes over this side, it will maintain the positive polarity. Okay, so what will happen is, when the negative side goes to that commutator, so the commutator at the plus side will always be touching with the coil that are under the north pole. Okay, the same thing with the negative end will always be touching with the commutator that are connected to the coil under the south pole. So that's why you have this shape, okay, whenever it try to changes, but we meet the end of the commutator, and therefore will be positive again. So that's why we need power electronics to make sure that you can filter out and come up with a DC voltages. Okay, so what happens here is because there are a drop in voltages lah kan, as the commutators shift between one commutator to the next. Okay, alright, so we will stop here for this week, and I will continue with the rest of the DC machines next week.